Okay, so NVIDIA, of course, is well known for our presence in the graphics and gaming space, right? We started as a graphics processing unit company. We made GPUs. And I chose a couple of marketing slides to represent who NVIDIA is. This is one of them. And thank you. Great. So this is a demo that we showed just a couple weeks ago at the Game Developers Conference. This looks like a film. It looks exactly like a film. It's actually a video game. It's a collaboration with Epic and ILM, and it looks completely realistic. This is what the future of games looks like. And so graphics and gaming, very near and dear to my heart, very near and dear to sort of what NVIDIA comes from. But in a machine learning conference, the other marketing slide, this is a stop motion animation, actually literally stop motion, physical, is our latest product. So in a machine learning conference, people are going to think of NVIDIA often in the context of machine learning, right? We build the silicon and much of the software that powers sort of the current sort of AI revolution. And so this is our latest product. It's pretty exciting. It's basically 16 of our highest end GPUs hooked together with this very high-speed switch fabric that lets you essentially program them as a single one. So it's kind of like a 2 petaflop, half terabyte of high bandwidth memory, 350-pound GPU. And there is a line of people out the door. We can't build these fast enough to sell them to all the people who want them, because there are some people who want to solve problems that you just can't solve any other way. And of course, we also make smaller GPUs. Many of you probably have them in your machines if you're doing machine learning. Oh, thanks, even better. Okay, so you might wonder, do these things conflict, right? Is NVIDIA no longer a computer graphics company? And of course, that's not the case. My whole thesis here is going to be that machine learning and computer graphics go together like peanut butter and jelly. And I'll kind of reiterate that. And that's for a reason, right? The whole reason why the things that make GPUs good for deep learning, things like massive parallelism, accelerated convolutions and tensor operations, mixed precision, all of these things were things that were there because you need them for graphics. So there was a very natural synergy there. And now it's going the other way. Now that we are consciously evolving our GPUs to be good at to be better at machine learning and deep learning, we're finding all kinds of interesting ways that we can use machine learning as a tool for computer graphics and image synthesis. And so the rest of this talk is going to be this kind of high-speed tour of a whole bunch of examples of interesting ways that we can use machine learning to generate, cool, hopefully beautiful pictures. And I hope that you'll get, some of these you will have seen, some of them you probably haven't. I hope that you'll leave with sort of some insight and maybe an appreciation of how some of them work. So I'll start off talking about texture synthesis and style transfer. So texture synthesis, first I want to talk a little bit about how convolutional neural nets work and how they kind of represent an image. And many of you probably work in this field and understand this stuff deeply. But if you take a deep neural network and you train it by showing it ImageNet or millions of images, it will eventually build up a representation across all the different layers of that neural net. So the various weights of the various neurons, the various layers will represent the image in some, we'll sort of take an image in and represent it in some fashion. What you find is that the first layers tend to have these sort of very low-level computer vision style operators, things like edges and corners. And then as you get deeper into the layers, you start representing sort of higher and higher level features or concepts, things like texture, shape, and eventually even sort of semantic concepts like that's a cat, right? You can build a network that will have a neuron that says that's a cat. Let's think about how, I want to talk about texture, sort of texture in the sense of, the appearance of a material or a collection of materials. In this case, it's a photo of some potatoes, right? How does a convolutional neural net think about or see that texture? Well, it represents it as this sort of pile of features at different levels, low-level features, high-level features, right? And if you wanted to know sort of what does that look like, what does that pile of potatoes look like, one thing you could do is you could capture sort of a statistical fingerprint that consists of some sort of statistical summary. In our case, we use covariance of these features at these different levels. And so this gives us a way of describing what the or a way of sort of representing inside this neural net what this what this patch of texture that I'm calling the exemplar, what that kind of looks like at some level. So what's interesting now is you can reverse this process. You can give it, because this whole thing is differentiable, right? We can give it a patch of random noise, just a bunch of noise, and we can enforce, we can basically use stochastic gradient descent to evolve this image, this noisy image, into something that has or matches those same statistics, that has an image that has the same statistical fingerprint. And so we can evolve, as you see, this field of random noise into something that looks quite a bit like a pile of potatoes. So this is texture synthesis, and it's already useful. This is already something that's very useful for computer graphics, because if you're an architect or a video game designer, you're making a building, you've got a rock wall, you don't want to have to pay an artist in Photoshop to sit there and draw a rock wall or carefully sort of paste together pictures of a rock wall. You'd like to be able to just say, cover this with rock or brick or denim, right? Whatever your material is. And I'm going to talk more about material in the next section. So this is useful. We can just give it a field of random noise. It'll evolve something that looks a lot like rock, or brick or denim or potatoes. And so this is a fun trick. It is useful, as I said. It gets really interesting when you get to examples like the one on the right, right? Making an infinite field of pasta is cool, but being able to, what you can do is instead of taking a random image and evolve it to look like pasta or potatoes, take an existing image. In this case, it's a computer graphics image. That's a classic computer graphics image called the Cornell box. It's one of our sort of very simple test scenes that we use to test the way the light bounces around a scene. And then we're going to evolve it to have the the statistical fingerprint of a target image, in this case, the scream. And sure enough, we can evolve that image to have that kind of style. And so this is called style transfer. And you've probably seen examples like it. There's tons of them out there. Here's a website that I kind of like. It's in Russia, and and people sort of upload, try out and upload various things. And there's some really stunning examples. I think this is a genuine art form, right? This is a person and a machine collaborating to make an image in a really new way. And I think there's some very creative examples that people have come up with. I love all of these. Here's the website itself. You can't read it down there. Not entirely safe for work. Not everybody who uploads pictures of this has good taste, but there's some amazing artwork on there. It's called ostogram.ru.Russia. Ostogram, like Instagram, ostogram. I think these slides are available later, right? And you can actually evolve this to run in real time. So here's an app that does this fast enough that it can actually keep up with the video feed. And so this is, I don't have a video, but this is one frame of a stylized video feed, which is pretty fun to watch. Okay, so let me go back to this question of materials. And I want to give you kind of a very fast example, overview of a way that we're using networks and interesting ways to help capture materials. Now materials, if you do CGI for movies, for example, or you're an architect, again, you're making a demo for your client, materials really matter, right? Without materials, by which I mean things like wood and leather and metal and denim, then they might look interesting, but it doesn't look very real. So the problem is that real world materials have enormous variation. They're very complex. And not only do they have a certain color and do they reflect light in a certain way with a certain kind of glossiness or not, there's a lot of spatial variation. And that's what really gives the material its look, right? So here's a close-up of some wood. Let's take an example of this, this white leather sofa. And if we zoom in, we see that its appearance is really caused by the sort of microstructure and what we call mesostructure of the little bumps on the surface, right? So we can take this close-up photograph of the surface, and we can create this patch, and we can say, oh, that's our exemplar. Can we generate more stuff that looks like that? Well, yeah, I just showed you how, but it turns out that it's not going to work very well if that's all we do, because you won't capture the sort of three-dimensional nature of this material. It won't look real, it won't look three-dimensional if it doesn't reflect light from different directions to different directions like real leather does. So there's sort of there's a three-dimensionality here. So we need to capture not just the color, but also the structure of it and how it reflects light. Okay, so here's how people do this normally. They build this giant rig, that takes photographs, that has cameras all over and lights all over, and they take lots of photographs with lots of lights from different angles. And a rig like this is 10 feet high and takes a lot of power and costs a lot of money. It's clearly not something, movie studios can and do build systems like this, but it's clearly not something that a 1 or 2 person architecture firm, for example, would be able to build. So let's go for something much, much simpler. Here's an iPhone, and it's taking a picture with the flash on, one picture of a material, right? In this case, it's red leather. And so here's that material. And the thing I want to point out is that in this one photograph, we actually have a lot of information about how this material reflects light. here's a shot of it being lit from the upper left. Here's a shot of it being sort of lit frontally, and so forth, right? So different patches of this image contain information about how this material reflects light. Now, in computer graphics, a little dim there. In computer graphics, we represent this with a series of maps, and these are sort of the terms we use. We talk about the diffuse albedo, which is basically the color, the specular albedo, which is the color that it reflects, that the specular highlights have, the glossiness, which controls sort of how tight or broad the specular highlights are, and the normals, which are sort of about the shape, structure, what direction the surface is facing. So we're going to build all these maps, and what we want to do is take this input photo, and we want to somehow hallucinate what's called an SVB-RDF, basically a reflectance model, a model of the reflectance. We want to synthesize one that can, when it's rendered, when it goes through a rendering pipeline, turn into an image that has the right characteristics, has the right color. So we do this process, and the neat thing about this is that now this is no longer just a single static set of colors. It's actually a full material reflectance model, so it can change shape and color as it's being lit from different directions. And you see that we've correctly captured the way that this thing reflects light, right? So we can sort of move this, slide this patch around and re-render it, and it'll have the right color, even with the specular highlight and so forth. And so here's the process at work. We're going to do something very similar to what we did before. We're going to take several patches, and we're going to render all of them. And we're as we evolve that material, as we sort of move that material by stochastic gradient descent toward something more realistic, and eventually we get something that fits in. And you can't even probably see the seams on this projector. You probably can't even see the seams. All of those materials fit in so well. So this process took a couple hours at the time. Today you could probably do it in a few minutes. What I want to show now is here's the key insight, and here's where this all comes back down to machine learning. The real problem here is we want a system that can basically say, does this patch of rendered surface, this exemplar, look like this patch from the photo? Okay, that's the looks like problem. It's the kind of thing that people are good at and computers traditionally are bad at, right? More mathematically, you could think of this as saying, I want some function which tells me that the distance between these two patches of brick texture is roughly 0. In other words, they almost look the same, despite the fact that if you actually subtracted them pixel by pixel, you'd get something very non-zero, right? They're not the same. They just look the same. How do we do that? Well, you guessed it. We're going to represent them with some sort of statistics that we're going to extract from running them through a convolutional neural net. And so if those statistics are roughly 0, then these two patches of brick look the same at some level. And so skipping a whole lot of math, the long and short of it is this is a rendered material. It's not the real thing. It looks completely realistic. And we've done a good job of capturing this material, again, from a single iPhone photo instead of a $100,000 rig of cameras and lights and LEDs. And the key insight here is that we're trying to fuzzily match two images in terms of how similar they look, but without comparing pixels to pixels. And by the way, doing so in a differentiable fashion so we can stick it into a standard optimizer and just have it evolve kind of automatically. All right, so shifting gears again, I want to talk about enhancing images. I told you this is sort of a lightning tour. There's a network architecture called an autoencoder. And basically it takes an image and learns to represent it. It's sort of, the top half of this hourglass kind of encodes the image down to a sort of a terser representation. And then a decoder that decodes that image, reconstructs it from that terse representation, and with access to the various neural weights and pixels of the original, into the same image. So a network that takes one image and turns it back into that image isn't very useful. But you could do interesting things with this if you train it to recognize not just the image, but also the image plus something else. So we're going to add noise to this image, and we're going to train this network to recognize noise. And as you'll see, I actually define noise very broadly. And so now the top half, the encoder learns to represent images and detect noise, and the decoder learns to reconstruct those images without noise. Okay, there's a denoising autoencoder. And so in this case, the noise, what I've done is I've trained this autoencoder to really dislike this font in all sizes and colors. Okay, it hates this font and it wants to get rid of it. And so I can feed it an image it's never seen before, corrupted with this font all over the place, and it'll reconstruct it. Right. So here's a slightly harder example. Click. Click. Here's a harder example. This one's harder because it has a bunch of colors and a bunch of bright colors. So you might have been like, oh, it's just detecting skin tone. No, it's detecting the font. It also has a bunch of letters that are in a different font and so will be preserved. So I find this remarkable. It's not perfect. If you really look, you can find a couple places where a little bit of a Y survives, or an X, but it does an incredible job. And if you look at like where it says CR on the red bike, kind of in the middle of the screen, underneath that it says 250 milliliters. And if I can't even see that, and it's able to reconstruct. So this is kind of CSI kind of stuff. Enhance, zoom in, enhance. This is remove the noise, get rid of the font. And it works for other kinds of noise, right? Like JPEG artifacts, right? So here's another one of those kind of classic Kodak, images, and we've JPEG'd the crap out of it, right? The left-hand image, this looks like crap. The right-hand image, goes through the autoencoder, comes out looking pretty good. Is it perfect? No, right? It can't do miracles. It can't reconstruct information that it never knew about, but it can hallucinate image pretty remarkably. Here's an extreme example of that. Okay, we took the JPEG and we cranked it all the way. This is all the JPEG that there is applied to this image. And there's the result. So this is kind of a cherry-picked example, but it's a real result. It's a good example. This works for Gaussian noise and Poisson noise, and that might be interesting to you because if you know anything about how cameras work, that's essentially what you get when you have very low light. A shot noise in a camera kind of has that characteristic. So you can use this as a denoiser for low light. And now we can start doing tricks like actually enhancing the image. So this is taking the image on the left and using an autoencoder to create an image with 4 times as many pixels, right? Twice as many pixels in X, twice as many pixels in Y. And it works essentially flawlessly. Here's a more extreme example that doesn't work flawlessly, but it's still very impressive. Now we're going to create 4 times as many pixels in X, 4 times the resolution in Y. So we're creating 16 times as many pixels. Works pretty well. A few more examples. So this image again, sort of a 16x upsampling. This works particularly well for vector art, and you can imagine this is interesting to companies that might want to like re-release assets. You're porting some game, right? And now it needs to run on a 4K screen when before it was operating at HD or pre-HD. So that kind of result is really useful. And so these are actually all tools that are available on NVIDIA's website that we encourage developers to just download and use. It works for natural images. And it works for a particular kind of noise that you get when you do what's called a Monte Carlo render. And if you're a person who does CAD who makes uses film tools or makes sort of real high quality predictive renderings, this characteristic of noise. The way these things work is they do this technique called path tracing, which is correct and provably will get to the right answer over time. But it starts with a very noisy kind of salt and pepper image, and it takes a long time for those images to converge to reality. And so film frames take a really long time, in part because they're just waiting. They're shooting enough rays, shooting enough paths to get rid of this noise. And we can sort of shortcut that process and let the artist, the director, the lighter see what it's going to look like much more quickly by using a deep network. This actually ships with one of our tools. This is a real-time demo. This is actually a real-time scene. You can fly around, and while you're flying around, it's kind of salt and pepper, and you let go of the mouse and it goes zoop, and in about 200 milliseconds, it's a nice, clean-looking image. All right, shifting gears again. I want to talk about facial animation. So humans are really good at faces, right? We look at faces all the time. We know what they look like. We know how they move. And so getting facial animation right is, a really hard problem that they struggle with in film, and these days they struggle with in games. So here's an example from a recent AAA game, Quantum Break, a company called Remedy, that does a pretty high-end pipeline. They have 9 cameras filming the person. The person's in the sound stage. They're reading from the script. They'll read every line many times with different facial expressions because they might have to deliver the character, the avatar might have to deliver that line, when it's in pain or when it's angry or when it's happy. So they're going to read all these lines. It's actually a grueling job, and we're going to film this from 9 different cameras, some in black and white, some in color, and then there's going to be literally hundreds of hours of artist cleanup time. Hundreds of artist hours to clean this up and make a high quality mesh. And so our ideas was a couple years ago, was to work with these folks and use those hundreds of hours of effort as our ground truth and see if we could train a deep network to do the same thing, but from a single camera position. So in other words, having done all of that work, having the artists having done all that work, can we exploit that to take something where now we can take footage of the same actor and maybe with 5 minutes of training on a new actor and pump that into a network and have the network produce the 3D facial mesh that is then animated for the character. So here's an example of the system. So on the left you see the footage from the center camera, center of those 9 cameras. The guy's talking. In the middle, so that's the actual stream of images from the camera. In the middle we see the capture pipeline used by this game studio. Okay, this is 9 cameras, optical flow, and again hundreds of artist hours to do this sort of manual cleanup. And on the right you see our system, which runs completely automatically off of a single image and achieves really just as good a result as all those hundreds of hours of artist time. Remedy is super happy with this. They use it in game. They're using it in production for all their games now. This part has worked very successfully. And if we can do facial performance capture from video, that raises some interesting possibilities. Can we do it from audio? Now think about this. All of that. Hiring a name actor. With a contract from Hollywood, having him or her read all these lines. That's very intensive, right? Suppose you then want to release it in another language, right? You're not going to hire another actor and have them and do all this work again. Even though we've accelerated this process enormously, you're still probably not going to do that for localization into lots and lots of different languages. And furthermore, there's going to be a lot of secondary characters, or even player avatars, people who you can't pre-record because you don't know what they're going to say in advance. So if you could drive facial animation from audio, that'd be super useful. And again, what we did is we essentially chopped off the top half of the network, the part that took in the video, and replaced it with a new network that we trained to take in audio only and again generate sort of plausible responsive facial animation. Here's an example.
Chaps or jolly earth-moving headgear.
Let me play that again, now that we got the audio. On the left is the performance capture, the video-based performance capture. This is basically ground truth. On the right is audio only. It has no idea what the person's doing or saying. It just gets a soundtrack.
Are those Eurasian footwear cowboy chaps or jolly earth-moving headgear?
What the hell is he saying? So this is like the quick brown fox jumps over the lazy dog. There's a bunch of expressions that kind of work through all the phonemes and visemes that they have. When you do this kind of work, you have your actors say, and you have them say them in all these different emotional states so that you can record that. I'll get to that now. This kind of raises the interesting question: what face should the person make when there's silence? Like, are they happy, angry, sad, in pain, asleep? So, to deal with this problem, we added an expression descriptor, a small vector of how happy, how sad, how much in pain, how surprised, and so on they are, and we feed that into the network as well. It sort of conditions the network. So, and so here's the network we built. And there's of course a whole paper about this and a lot of math. We take the expression descriptor, we feed it into the network, and in the end, audio goes in, and 5,000 three-dimensional vertices that represent the different points on the face come out. So it's audio to mesh. Here's the final result, just to give you an example of something from the game with the textures. The eyes will look a little funny. They weren't used. They were done in a separate post process by a different part of the game engine. So the eyes might look a little funny to you. On the left again is ground truth. On the right is audio only.
Listen up. The train yard warehouses is our main objective. Alexei, you and your men will do that. You have to go in and out very quick. I want you to get all the ammo and weapons that you can carry and come back as quickly as you can. You understand?
Now, the one on the left is better, right? There's much more emotion. The actor is doing this thing with his chin. He looks stern, like he's emoting, in ways that are not captured in the audio stream. But I would argue that the one on the right it's plausible, it's responsive, it looks realistic. I'd say that's absolutely good enough for a secondary character localization into obscure languages that you're not otherwise going to be able to support at all. And so we're really happy with this result. Click. What's interesting is once you've trained this, you can actually feed in different speakers, and it does quite well. So this is my boss, Jensen Huang. He's the CEO of NVIDIA. He's launching one of our GPUs a year or two ago. And we just fed his audio straight into the same deep network controlling the same mesh.
It's the world's first 16 nanometer FinFET GPU in production. World's first.
And again, I want to show you an example of sort of generalizing over different expressions. So here I am sort of sliding that vector around, between happy, sad, surprised, angry, in pain. And now we're going to show Jensen again launching that GPU, but this time he's going to be in tremendous pain.
It's the world's first 16 nanometer FinFET GPU in production.
And it does pretty well with languages. You would get a slightly better result if you trained it specifically with somebody speaking that language, right? But here's what happens if you take that English language capture and feed it into, and feed it with a soundtrack of somebody speaking in a different language.
Chacun peut se prévaloir de tous les droits et de toutes les libertés proclamées dans la présente déclaration.
すべての人は人種、皮膚の色、性、言語、宗教、政治上、その他の意見。
All right, let's move on to character animation. So faces are important, but the other thing we're really good at is understanding the way that people move and walk around. And it turns out walking is really hard. Okay, so this is what happens if you take a robot and you train it with a state-of-the-art reinforcement learning, sort of bare physics, use a nice high-quality reinforcement learning algorithm, and give it the goal of sort of locomoting around just sort of from scratch. From first principles, this robot's going to learn to walk. And what you get is the Ministry of Silly Walks. I mean, this poor robot, it's kind of figured out how to move, right? It kind of holds it, puts its stance out and it wiggles its arm real hard and it kind of throws it off balance and it lurches forward and backwards, But this is a pretty, this is a pretty tough way to learn to walk. And yeah, so this poor guy. However, if you take an interesting new innovation, a new network architecture, and you feed it with hours of motion capture clips of real people walking and running and stepping and jumping and ducking and crouching and falling down, you get something much more realistic. So this is really cool work. This is completely controlled in real time. A video game character walking around uneven terrain, with no planning or anything else. And I think this looks remarkable. And if you've ever played like a game like the Assassin's Creed, I think what series where this character comes out of, this looks really good. It looks much better than anything that's been seen in games before. It's running in real time, very lightweight. In fact, once we've built this network, it's so lightweight that we can run lots of them. Like GPUs are good at inferencing on networks, right? So we can have tons and tons of characters all milling around running this network to figure out where to put their foot next. But this is a little unsatisfying too, despite the large crowd, because the characters aren't interacting. In fact, they're passing right through each other, and the physics isn't great, right? I started with pure physics, and I've taken away the physics, and I've gone strictly to motion capture. It looks better in some ways, and it looks less realistic in other ways. So you'd say, well, let's combine physics and characters with intention, and combine that with some of these techniques. And this is a pretty fun result. So these characters are interacting a lot. They're basically playing like freeze tag, like running away from each other, running toward each other. I think they're literally playing tag. I think that's what the reinforcement learning has been fed. It's fun to watch. All right. So last part of the talk, digital humans. So we've talked a lot about various ways that we can sort of enhance computer graphics and the models that we use in computer graphics using machine learning. I want to talk for a second about creating pictures of humans completely from scratch with no 3D models, no notion of what a human is or looks like or how the skin reflects. A lot of you have probably seen this work. This kind of went viral. These are a bunch of pictures of real people, real celebrities. Okay, you'll recognize some of them. So real people, these are just scraped from the web. Somebody in Hong Kong went and scraped like 30,000 pictures of celebrities off the web. And what we've done is actually enhanced that data set, taken the best of them, using the super resolution techniques that I talked about to make higher quality images, aligned them so the eyes are in the same place and the face is vertical in all of them. And so now we have a data set of tens of thousands of pictures of real celebrities. And we're going to feed that into a network. This is an architecture called a GAN, Generative Adversarial Network. GANs are very powerful, but they're very unstable and very hard to train. We're still kind of figuring out how to make it work. And the big accomplishment that we showed here was that we can actually generate random people that are completely artificial, but look, in many cases, very real. So these are all literally just, there's a random vector with 1,000 parameters, or there's a vector with 1,000 parameters, you set it to random numbers, and it generates a face. Pixel by pixel, right? It doesn't know what a face is. It doesn't know that people have 2 eyes and a nose and a mouth. It doesn't know anything about hair or facial or skin tones or the catch light. You know, it's actually doing the catch light in the eye and the eyes correctly. It doesn't know any of that stuff. You'll see there's some monsters that creep in. Right? It doesn't always work, and not every space in this giant not every point in this 1,000-dimensional space generates a real-looking human. But some of them, I'll just show that real quick one more time, if I can. Click. Some of these pictures look really, really good. All right, I'll skip. Okay, so the key insight that we had here, in case you're curious, was to train these GANs progressively. The problem with GANs is that they tend to not scale up stably to large resolutions. So we start by training them on low resolution, where it's just really, all it's got to do is get the skin tones in the right place. And then we gradually crank up the resolution, and after hours and hours and hours of training, it gets better and better. And you see, you'll get more realistic. And so we're going to zoom in on just one of those random numbers. Think of this as like a point in this 1,000-dimensional landscape. And as the network trains, the exact image it generates flickers between male and female and old and young, but it more or less stays the same, right? It's kind of interesting. And that gave us the idea that it would be interesting to take random spots in this latent space and sort of interpolate between them. And so that leads to what we call interpolating celebrities, or nightmare fuel. And again, this is a set of random numbers that's changing smoothly. There's just a vector in this 1,000-dimensional space. There's some monsters in there, but there's also a lot of really compelling images. You know, so I find this fascinating. It's really fun to watch. This is kind of hypnotic. By the way, there's a full hour of this on YouTube if you're curious. We actually set that up in the hallways of one of the NVIDIA offices, and people would just stop and stare. And yeah, there's something very nightmarish about, you know, beautiful people suddenly turning into like their mouths expanding into a whole new face, or their hair kind of like, you know, catching fire and morphing into other people. All right. So this is not just I mean, this is a parlor trick, what I've showed you so far, but it does raise really interesting possibilities for image editing. You know, so you can imagine keeping one part of an image solid and trying to paste in something else. You want to paste in somebody's mouth, you know, or you want to, in this case, we're going to take two different halves of a photo and paste them together, and the GANs are, you know, essentially will interpolate at the right levels of the network, and we'll get this kind of mixture of people. And so this is quite interesting to watch. So the left half of the face is going to remain the same, almost. But notice that it is responsive. It's not just like a cutscene. For example, if you look at her lips, they will open and close as the right half undergoes variation. Creepy. Creepy. All right. So one last example. This is the extreme example of this. So just some random guy who is a personal trainer in Germany, and he put an interview of himself, with like a 30-minute interview on YouTube. And so we took and ingested all of those video frames and tried to get the system to produce a video rather than just a still image. And I hope you can see that. It's okay. So again, the computer doesn't know what people do. It doesn't know what a face is. It doesn't know anything. It's just sort of generating believable frames in a video that sort of smoothly blend to each other. So the guy never made those particular expressions, right? You know, we just captured a lot of his expressions, so he makes expressions kind of like that. Not perfect, but pretty cool. Pretty interesting possibilities there. All right. So to wrap up, you know, we talked about using networks in interesting ways, using deep learning in interesting ways to power image synthesis, texture synthesis, material synthesis, style transfer, image enhancement, facial animation and character animation. These are just some of the many examples. There's a bunch more happening in my group. There's a bunch more happening all over the world. So it's a really interesting, cool time for computer graphics as we're sort of finding this interface with machine learning. And I really think that this is the future. I will predict that in the future, the job of the GPU will no longer be to make an image for your screen, for your eyeballs to look at. It will be to make something that a deep network will then interpret to become the image that you look at. In other words, the job will be to feed not the final image, but the deep network. And I think that's going to be a really interesting time in computer graphics. And I will remind you that, in short, all of these things fit together like peanut butter and jelly. So thanks very much, and if there's time for questions, I'm happy to take some. What do you think?
One or
two questions.
Two questions. All right. Two questions.
Oh, I see. Okay.
It better be good.
Wait for the mic.
Better be good.
Just be loud.
Better be good.
How long until the technology is better than the human brain at recognizing images, human faces particularly?
We're already there, in short. The question is, how long before the technology is better than the human brain at recognizing images, specifically human faces? And we've just crossed an ImageNet, human recognition. Now, of course, that's a test. You can believe it or not, and we just barely crossed it. But I would argue we're basically already there. That already computers are, certainly in certain circumstances, are getting better at recognizing people and things than people are. Facial recognition in particular, computers can do a remarkably good job on. So I would guess that we're already there. We're certainly close. And I see one more person with their hand up. TPUs or GPUs? I predicted this question. So TPUs, for those of you who don't know, Google has announced a chip that is sort of a custom-made deep learning chip. And it's called the TPU, Tensor Processor Unit. So obviously you should use whichever works better. I think that what you're going to find is that GPUs will continue to work better. GPUs run all the frameworks. So NVIDIA's kind of committed. Our strategy is to be sort of Switzerland, right, in this scenario, and support all of the frameworks. Run open. Run in your co-located, on-premises cloud server, as well as in Google's or Amazon's or Facebook's or Microsoft's. And so I think GPUs have a tremendous advantage there. I think TPU is interesting, but the thing is, we can build. The inside of our GPU looks a lot like a TPU, right? As I said, they're very similar. So there's really nothing stopping us from building, chips that compete very directly on these. So I think that you should use whatever you think is better. Whatever you find is better when you run the experiments. But I think what you'll find right now is that GPUs are way out in the lead in terms of performance per dollar, performance per watt, and they support all the frameworks. They don't just run on Google servers. So we like them all. We like all the deep learning.
Thank you.
All right. Thanks, everybody.
Thank you. Thanks so much. Awesome.